Okay, so since this unit is called the acid-base unit, we should probably talk about what happens when you mix acid and base together. And years and years and years ago, there was a Simpsons episode where Bart Simpson stole somebody's aptitude test, an IQ test, and basically said, hey, and erased the name and got a perfect score. So they sent him to the school for the talented and the gifted. And they were in science class and they had to like design an experiment, and Bart was like going to mix an acid with a base, and this professor or teacher or whatever came over to him and said, hey, do you know what you're doing? And Bart's like, take it easy, man. And then the teacher was like, okay, and then Bart was like, yeah, I'm going to mix an acid with a base, and he mixed together and blew everything up, and he eventually got kicked out of school because he admitted he cheated because the pressure was too much. But the truth of the matter is, when you mix an acid and a base together, that doesn't happen. When you mix an acid and a base together, what ends up happening is you form an ionic compound and you form water. So as a bit of an example, if we were to take something like HCl, which is a really common acid, and a base, NaOH, which is a really common base, so this is my acid and this is my base. And if I do the old double replacement reaction switcheroo scenario, right, I get something like NaCl, and I get something like HOH, which we talked about yesterday, is commonly known as water. This happens to be balanced the way that it is. But what I would like to point out is that if the acid-base neutralization forms an ionic compound and water, here's my water, and an ionic compound is a compound that's made up of any metal and nonmetal, which in this case is NaCl, which happens to be salt. So if you take hydrochloric acid and mix it with sodium hydroxide, in theory, you get salt water. But because we never eat or drink or taste anything in the lab, you wouldn't know that. But the data says that you do. So when we solve acid-base neutralization reactions, we start with a balanced chemical equation because we're going to have to do a very small stoichiometric calculation. We use the molarity equation to solve for moles, so that's step 2. Step 3 is we use stoichiometry to change substance. So we are doing a mole to mole calculation, and then we use the molarity equation again to solve for the final answer. And so it's 3 mathematical steps. None of them are incredibly complicated. It's just a matter of deciding what it is that the problem is asking you to solve for. So here we go. First example. The question is, what is the volume of a 0.5 molar potassium hydroxide solution needed to completely neutralize 0.075 liters of a 0.125 molar solution of hydrochloric acid? So part of the issue here is you have to kind of know what you're dealing with. So I have my acid side that I'm going to kind of focus on, and then I'm going to have my base side of this reaction. So in my acid side, I see that I have HCl, so I have a molarity of 0.125 molar HCl. I don't know the number of moles because probably won't tell me that, but I do know the volume in this case is going to be 0.0750 liters. Okay. On the base side, I know the molarity, right? So I already know the molarity, which is 0.500 molar. I also don't know the moles. But I also know, or I'm asking to solve for, yes, the volume, because it's asking me to identify the volume of the base that I need. Okay. So step 1 says solve for moles, right? So in this instance, I'm going to solve for moles of, in this case, acid. Okay. So I'm going to use my molarity formula. So if molarity is equal to moles over liters, and I know the molarity is 0.125 molar, and I know the number of moles is what I'm going to solve for, and I know the volume is 0.0750 liters. When I math that out, I solve for moles by multiplying both sides by 0.075, so 0.075 times 0.125. I get something like 0.009375 moles of HCl is equal to moles. Okay. Now, the next thing I'm going to do, next step 2, is do a mole to mole conversion of moles of acid to moles of base. So do a moles of acid to moles of base conversion. And so that's going to be a simple stoichiometry situation. So I'm going to take the 0.009375 moles of acid, HCl, and I'm going to go mole to mole, which is I'm comparing moles of acid to moles of base. Okay. And in this case, the ratio happens to be 1:1. So it's like 1 mole of HCl to 1 mole of KOH. They won't always be 1:1, but this time they happen to be. So 1 mole of KOH is equal to 1 mole of HCl. So the math on this one is super simple. It's simply 0.009375 moles of HCl. Or not HCl, that's silly. We're doing NaOH or KOH. All right, now the third step, step 3, step that comes after 2, is to solve for, in this case, volume of KOH. And so we're really looking for KOH, and we're going to use our molarity formula again. So molarity is equal to moles over volume. In this case, I now know that my moles is this value right here. So that's going to go 0.009375. So that's going to do this. It's moles of KOH. And we're, we know the concentration. I knew the concentration already is 0.500 molar. And we were solving for liters here. So math says that I'm going to multiply both sides by L and then divide both sides by 0.5. So I get 0.009375 divided by 0.5, and I get a concentration, a volume of 0.01875 liters is equal to liters. So that's my final answer. And again, I said this math isn't complicated, right? But it is multiple steps, and you have to know what to do when you're doing when you're doing what. Okay. So, questions about that so far? All right. Should we do a quick another one? Or do you want do you want me to do it, or do you want to do it? You don't want me to do it. You want to do it? No. You want me to do it? No. Oh gosh, because Oh man, tell you what, I'll do it in steps, but you do it. Okay, so ready, set, go. Chemistry. You don't remember what to do? I literally have notes you can flip back and look at. All right, so I'm gonna read my problem here. So we got and volume, no, not volume, liters, base, which we got molarity, we got moles, and we've got liters. And see, so we know some stuff about our acid. So we know that we have 0.100 molar, and we know that we have a volume of that to be something like 0.0650 liters. We have 0.0250 liters of our base, and we are asked to solve for the concentration of the base. So that's a little help. Moving on. Step 1. Solve for moles of acid. So we're going to use the molarity formula to solve for moles of acid. And we know the concentration is 0.100 molar. And we're solving for moles. And the volume is 0.0650 liters. And so when we calculate that out, it's 0.1 times 0.0650. And we get a concentration, or a number of moles, to be something like 0.00650 moles of HCl is equal to moles. Step 2 is convert moles of acid to moles of base. So we're going to use stoichiometry here. So we're going to take these 0.00650 moles of HCl, put that over 1, and we're going to go to moles of base. So our ACl is this, and our base is this. So our ratio is 2 moles of HCl for every 1 mole of CaOH2. So I'm going to set that up so my 1 mole of CaOH2 is on top, and my 2 moles of HCl on the bottom. So I'm going to take 0.00065, divide that by 2, and I get something like 0.00325 moles of CaOH2. Huh? Yeah. And then number 3, in this case, is solve for molarity of base. So I now know the number of moles is 0.00325, and I know my molarity formula is molarity is equal to moles over liters, and we're solving for the molarity this time. So I'm going to take the 0.00325 moles, put it on top, and the volume, which is 0.0250 liters, throw that on the bottom, and then I'm just going to simply divide And I get something like a concentration of 0.130 molar CaOH2. All right, so for those of you that are playing along, this is what I got. Okay. Now, I'd like to point out something that's really pretty important here. So, first of all, I used the molarity formula to solve for moles of acid, which we did before. Check. Step 2 is to convert moles of acid to moles of base, doing a simple stoichiometry calculation. This time the ratio was 2 to 1. So I had to divide the number of moles of acid by 2, and I got 0.00325 moles of calcium hydroxide. I then now had the number of moles of calcium hydroxide. I knew the volume that was used. So I was able to calculate the molarity to be 0.130. Now, here's the thing that's really important. In our step 2, okay, well, we'll come back to that, I guess. Yeah, we'll come back to that. All right, so in any case, so that's that. So any questions about that before we go on to titration and neutralization reactions in action, which is the lab that we're going to do next week, Tuesday. All right. So the lab technique that we're going to learn about is something called a titration. And a titration uses a device that is known as a buret. Basically, what you're doing is you take a concentration, you take a substance that you know the concentration of, you know it's like molarity, and you add it to a substance that you don't know the concentration of, you don't know its molarity. And we only usually do this with acids and bases. So we generally will take a base and we will add it to an acid. And when we do that, we're attempting to get it to a pH of 7. That's neutralization. By knowing that, by doing that, we are able to go ahead and calculate the concentration of the molarity of the substance we don't know. So the calculation that we just did is the exact same calculation that somebody would do in a lab setting. Hint, hint, wink, wink, nudge, nudge. Okay. Now, here are the devices that you're going to be using. One of them is called a buret. Burets are incredibly accurate, and they can read to 2 decimal places. Okay. Past, yes.
That's what?
The decimal point.
Well, is that like a liter or is that like a milliliter?
That's a good question. These generally are measuring in milliliters. So these are pretty accurate, so they can go to the hundredths place of a milliliter. Okay. We take the initial reading, which is going to usually be somewhere up here, and we're going to take the final reading, which will be somewhere down here. I should have maybe done this. My initial and then my final. Okay. And by doing that, we can go ahead and figure out exactly how much solution that we have added. So this is what a setup might look like. You might have a ring stand. You might have a buret clamp. You might have a buret that has a valve on it. The valve has a very special name. It's called a stopcock. And then you have a flask. And then you have something called the analyte, which is the thing that we are trying to determine the concentration of. And inside the buret, you have something called a titrant. So if our initial reading is way up at the top, here's our initial reading again. Our final reading might be somewhere at the bottom. And the endpoint is where the indicator changes color. So this is our endpoint. And at the endpoint, moles of acid equals moles of base. So moles of acid and moles of base are equal when you have reached the endpoint of a titration. That is when the titrant or the analyte changes color. So the thing about a buret is that it's opposite of what we're used to in terms of reading. We usually read from the bottom up, but we're going to read from the top down. See how the number goes from 12 to 13 to 14 going down? So when I read my initial reading, So when I read my initial reading over here, I might say that it's 12.56 0.6 because it's a little bit more than 12.6, but it's not quite 12.7. So I'm going to say 12.68 milliliters, right? So this is like at the beginning. And then at the end, I would say that it's 18.1234. It's a little bit more than 4. It's not quite 5. So I'm going to say 18.4, I don't know, maybe 8 milliliters. So how much was actually added? Well, that would be simply 18.48 minus 12.68 to give me 0, 8, what is that, 7? That's 5, 5.8 milliliters. Did I do that math right? Hopefully. I think so. All right. So that's how we get our value that we've added. So we always have our initial and our final. And so now we have an example of doing basically the same problem, except it's in a lab setting. So we have a student uses titration to find the molarity of the hydrochloric acid. The student titrated the hydrochloric acid with a 0.121 molar potassium hydroxide solution. Using the data table, calculate the molarity of the hydrochloric acid solution. So here are some things that we know. We know that the molarity of the KOH, so our base, right? I don't know what letter I'm trying to draw there. So we know that the molarity of the base is 0.121 molar. We don't know the moles of the base, but we can probably calculate that. And we want to find the volume of the base. So in order to do that, I'm going to take my initial volume of KOH minus my final volume. So I'm going to do that, I guess, step first this time. So 1, find volume, of base used. So I'm going to take the 39.52 milliliters minus the 23.65 milliliters to give me, let's see, 39.52 minus 23.65. I used apparently 15.87 milliliters. Now, the issue is that that's in milliliters. And when we do these problems, they have to be in liters. Okay. So now for step 2, I guess, is convert ml to liters. And you know that you should remember that the conversion is 1,000 milliliters is equal to 1 liter. So if I take my 15.87 milliliters and I convert it, 1 liter, 1,000 milliliters on the bottom, I get something like 0.1587 liters. So that's the volume that was used. So now my third step, step 3, will be to find moles of base. So we'll use our molarity formula. Molarity is equal to moles over liters. We know the molarity of the base is 0.121 molar. We are looking for moles, bless you. And we know the volume, the liters, is 0.01587 liters. So 0.121 times 0.01587. I get a number of moles to be something like 0.00192027 moles of, in this case, my base, which we said was KOH. Okay. Next step. Convert moles of base to moles of acid. So that's going to be our stoichiometry step. So I'm going to take the 0.0019227 moles of KOH, and I'm going to compare it to the acid. So the ratio is 1 mole of KOH for every 1 mole of HCl. And yes, I know some of you are saying, but V, when it's a 1-to-1, do I have to show the math? And the answer is yes, you do have to show the math. So I'm going to put that over 1. And I'm going to take my 1 mole of HCl and my 1 mole KOH. And I'm going to get my 0.0019227 moles of HCl. Step 5. I guess we should probably figure out what we're doing with our acid over here. So here's my acid, and I'm molarity and stuff, and I want to know moles, and I want to know volume. So in this instance here, I have to figure out how much HCl was used. So we're going to go ahead and we're going to find, I guess in step 5, find volume of HCl used. So that will be a little simple calculation of the 10.97 milliliters minus the 1.56 milliliters, which will give me 9.41 milliliters. I am running out of room, but I feel like you have more. So what I'm going to do next is I'm going to just kind of do some of this stuff off to the side or something. So step 6 is convert milliliters to liters when 1,000 milliliters equals 1 liter, right? So I'll do that over here in the corner. 9.41 milliliters, 1 liter, 1,000 milliliters gives me 0.00941 liters. So now I know the volume, which is 0.00941 liters. I know the number of moles because we converted that is the 0.0019227. And the problem is asking me to solve for molarity of acid. So got to find a spot to do that. So I guess I'm going to try to do that up at the top. So step 7, find molarity of acid, where our molarity formula is moles of acid over volume. So, So molarity, we figured out the number of moles of acid to be the 0.0019227 moles. And we found the volume to be 0.00941 liters. And so when we calculate all that business out, we get a concentration, and I'm going to actually move this over. I'll rewrite that. We get a concentration that is 0.2040669, But with 2 sig figs, or 3 sig figs in this case, the molarity becomes 0.204 molar HCl. So that's a lot of steps, I guess. But it's not complicated steps. I think it's just keeping track of what the problem is asking you to do. So there's that. So any questions about what this is asking you to do? Because this is a lab thing. This is something this is a set of calculations you're going to have to do in your lab next week. So I highly suggest that you get this copied down if you haven't done so already. Also, you're going to have a homework problem like that coming up. Okay? So, questions? All right. With that in mind,